Alright, so we have our stopper or whatever moving around in a circle, so that's considered circular motion. One of the things we want to look at is the velocity. So let's say this is moving around at a constant speed. Even though it's moving at a constant speed, what I want you to notice is at this location, let's say it's going clockwise, at this location our velocity is pointed north. At this location though, our velocity is pointed east. And at this location it's pointed south. And right here it's pointed west. So even though it might be moving at a constant speed, what's happening to the velocity? It's changing. Yeah, and why is the velocity is changing? Why is the velocity changing? What is velocity? It's not just speed. What else? Nicole?
Because there is an acceleration.
Okay, the velocity is changing because what's changing?
Velocity is a vector, so the direction is changing too.
Exactly. So the velocity is changing because the direction is changing. So even if the speed is the same, the direction is changing. Therefore, the velocity is changing, and therefore, Nicole mentioned, there's going to be an acceleration. That's what acceleration means. Acceleration means changing velocity. So there's going to be a acceleration. Now the name of this acceleration is called centripetal acceleration. Okay, centripetal. Centripetal is going to, the word centripetal, well, let's see if we can figure out what the meaning of the word centripetal. It tells us the direction of the acceleration. So let's look at this point. Notice here we're going north, and eventually we're going to be going east. So there has to be an acceleration to get us to go east, right? The stopper's moving up. Something's going to have to push it to get it to go east. Well, what direction should that push be? It should be east, right? So there's going to be a push this way that's going to provide an acceleration in that direction. Well, what about at the top? Well, at the top we're going east, right? And something's going to have to push it to get it to eventually go this way, right? To go south. So what direction is the acceleration right here? South. Okay, and so forth. So this one's going to push it this way, right? And this one is going to try to get it to go north, so it's going to push it this way. So what do you notice about all four arrows? What's the similar? They're all different, north, south, east, west, but what's true about all four? They're all pointing towards the center, exactly. And that's what the word centripetal means. It means center seeking, meaning it's seeking the center or pointing towards the center. And so that's kind of an important concept, that the acceleration is always going to point towards the middle. Now you could have figured this out a different way if you just think about the fact that what's the thing that's keeping this in the circle? What's the force that's causing this to go in a circle? The tension in the string, right? If I remove the string, is this stopper moving in a circle? No, it's not going to move in a circle, right? And so this is what we call a centripetal force. Centripetal force, because, well, if we know F equals ma, if there's an A, there must be an F somewhere. And in this case, the force comes from the tension in the string. So we call this a centripetal force. This would be, again, the center seeking or force towards the center. And I'm going to write it like this. Force towards the center that maintains our circle or circular motion. And kind of this word centripetal force, it's more like an adjective. It's not like that's the actual force. There's always some actual force, or what we might call an agent, that causes it to move in the circle. So I'll clarify that. So this describes another, I'm going to just quote unquote true force. So for example, in this example, what is the actual thing keeping it in a circle? The tension in the string, right? So the tension is, so we'd say the tension is the centripetal force that keeps it in a circle. So centripetal force that describes some other force. Let's take the moon and the earth. What's the force that keeps the moon going around the earth? Gravity. So we'd say gravity is the centripetal force that keeps the moon going around the earth. All right? So centripetal always describes some other force. And we'll talk more about that as we move along. All right, let's look at some of the equations here. So the acceleration equation, I'm not going to derive it for you. I think your book does, so if you want to see the derivation, you could go ahead. So A is just going to be A sub c, centripetal, that just stands for centripetal acceleration. Or if you want, you can think the c of the circular acceleration. This equals v squared over r. V squared over r. So what is v? That's easy, right? That's the velocity, how fast it's moving. And what do you think r is? So it's going to be kind of the radius of the circular path that's been being taken. And usually it's kind of obvious. I mean, in this case, it's basically the length of the string, right? That would be our radius here, r. Okay. Notice is the v. Yeah.
What are the units for radius? Does it depend on each one?
So what are the units for radius? Good question.
Meter.
Meters. And notice what does happen to the units. If you have a v squared over r, that would be meters per second squared, right? Meters squared over second squared divided by meters. And what are you left with? Meters per second squared, which is what we would expect, right, for an acceleration. So notice as this is spinning, if I spin it faster, what should happen to the acceleration? It increases, right? So the faster it spins, the more it's going to have to accelerate to change its direction, right? If it's going faster and faster. If it's slower, it's pretty easy to change its direction. It's not moving as fast. In fact, if the velocity doubled, what would happen to the acceleration? It would increase, right? But how much would it increase by? 2 squared times larger, right? So if it doubled, what would happen to A? It would quadruple. It would be go up by a factor of 4, right? Okay? All right. Let's go ahead and try a problem here.